Good morning and welcome. I'm Kelly Wicker, Director of the Science and Technology Innovation Program at the Wilson Center. Thank you for joining us this morning for the final panel in our series examining the impacts of last year's flurry of federal activity on semiconductor resilience and supply. Today, we're discussing the role of legacy semiconductors, and I'm really excited about the incredible lineup of panelists we have on hand to discuss perspectives from both industry and government. Before we get started, I want to remind everyone that this session is public and will be recorded, and our panelists' comments are their own and don't necessarily represent the views of their employers. I also want to invite the audience to submit questions using the Q&A box on your screen. We'd love the opportunity to address some of the things on your minds. I'm delighted to introduce today's panelists. Joining us today is the Honorable Nazak Nikakhtar, a partner at Wiley who served from 2018 to 2021 as the Department of Commerce's Assistant Secretary for Industry and Analysis at the International Trade Administration, and who also fulfilled the duties of the Undersecretary for Industry and Security at Commerce's Bureau of Industry and Security. We also have Andreas Schumacher, the Executive Vice President for Strategy, Mergers and Acquisitions at Infineon Technologies, Mark Garvey, President of the Global Business Unit for Advanced Technology Facilities of the Exite Group, and finally, our moderator, Don McClellan, who is the International Co-Chair of the Woodrow Wilson Center National Cabinet and a partner at BDT and Company. Don, thank you for leading today's discussion, and I'll hand it over to you to get started.
Great. Thank you so much, Kelly. This is a very, very significant topic. It's timely. It's also one where I think that the audience, you will get a lot out of the panelists we have today. The way I like to frame a discussion like the one we are about to have today on legacy semiconductors is, what's the what, what's the so what, and what's the now what? And our panelists represent those three dimensions, from the very practical physics and the background to legacy semiconductors, the definition of what we consider a legacy semiconductor, to policy and economic issues regarding legacy semiconductors in the world, and then the very practical, how do we make fabs? How do we catch up? How do we create the environment to produce those legacy semiconductors? So what we're going to do is have a conversation that describes what legacy semiconductors are, why they matter, how ubiquitous they are today, what the U.S. competitive issues are in and around legacy semiconductors, competitive issues, economic issues, national security issues, what it takes to build a fab, and why that's different from an advanced fab potentially, or why it's the same, timing and economics of that. And where should the U.S. spend its resources and energy vis-a-vis legacy semiconductor development? What advice for policymakers do we have at the local, state, or federal level? I'm going to ask Kelly if you could just bring up a slide as we think about the definition here, and I thank my colleague Andreas at Infineon for sharing this with us. And I'm going to start with you, Andreas. You know, we were talking in preparation that the definition of legacy, it might even be a misnomer. If you could maybe tell us how you think about that definition, help frame for us today when you hear the word legacy semiconductor, what do people typically mean? How would you want us to think about it for the balance of our discussion this morning?
Thanks, Don, and good morning, everybody. And perhaps the best way to get into this is to contrast this big tree of semiconductors, this huge variety, and I'm going to get into that in a moment, and start with the very top of this big middle trunk, where you see microprocessors, graphic processors of the 12, 7, and 2 nanometer feature size. And those are the ones which nowadays, for example, in national security discussions, the recent export control laws, which have been passed by the US and some of the allies, which are referred to as advanced semiconductors, or as Jake Sullivan has put it, even as force multipliers, and this is why they are under such scrutiny. But then if you look at the rest of the tree, which is then by definition non-advanced, or sometimes people like to talk about legacy semiconductors, there is such a huge variety. And I'm not going to go into each and every one of those trees, but just like to point out just a few, and I'll start with the bottom right, the power semiconductors, which are essentially electrical switches, and you need them to switch off and on electricity pretty much everywhere around you, save maybe for the mechanical light switch as you enter your or exit your room. So if you have an electrical car, if you want to charge this electrical car, if you want to steer the electrical car, or an airplane, or really any other electrical vehicle, if you want to run a conveyor belt, a motor on a conveyor belt, or if you want to convert the electrical energy which is generated by turning a wind turbine into the electricity which flows through the large high voltage transmission grids which span continents, all the way down to the 110 outlet which you have in your home. So that's the world of power semiconductors. You have memories, and they do pretty much what they say. They memorize or store information. Or you have sensors, and if many of you will have your cell phone nearby, you have, of course, audio sensors, a microphone. In fact, many microphones probably in a modern cell phone. You have, of course, the optical sensors, the camera. You might have temperature sensors, or other optical sensors if you wear a smartwatch which measures your heart rate. And I could go on and on and on. And the point here is that none of those branches are old branches which are withering away. You have super exciting advanced developments in the tips of all those branches towards the leaves. You have new material, exciting new materials in the power semiconductor branch. You can go all the way to quantum sensors on the sensor branch. You have lasers and LEDs when it comes to optical semiconductors. So a large market, of course, a large area of technology with so many incredible applications in our day-to-day life, for national security, for our industry, for electrifying our life. And I'll leave it at that, Don, and back to you.
Well, that's very helpful, and thank you for that. You did when we were talking earlier. We were talking about the physics of some of these characteristics that make it almost impossible to get them any smaller. One of the questions I know a lot of people ask is, if we have advanced semiconductors, why do we need the larger diameters? Why do we need these larger nodes? And it's because of the properties you indicated, the heat dissipation for power semis, or the optical properties for some of those circuits. I just say, as a follow-up question to you, Andreas, if you could kind of give us a sense, just kind of dollar-wise, cost-wise, or how much would some of these sensors cost, just so we get a sense, are these commodity that we're talking about, and what do we mean by that?
Yeah, I mean, just like the technologies span a very wide range, also the prices which have to be paid for those parts. Some of them commodities, some of them are highly specialized. You can get on the, I would say, in the tips of those, or in the branches towards the leaves, you can have sensors, you can have microprocessors or power semiconductors which go into the 10th or even 100th of euros, especially if you would, for example, apply other technologies like radiation hardening them for use in an aeroplane or in a satellite. So those can even run into the thousands of dollars potentially. And then you have very simple semiconductors which can be dimes or even nickel nowadays. And if you would open up your cell phone, which I don't advise you to, but you would probably find hundreds of them, and you can get thousands of them just in a little shot glass.
Yeah, some have said that the bill of materials by number of chips, not the dollar value, but if you look at the build of an iPhone, 60% or more might be these types of chips that you're talking about. Okay, so let me pause there for a minute, because as you said, some of these sound like they could be, I've heard one semiconductor manufacturer call it many to the penny that you're producing. Let me ask Nazak, bring you into the conversation. You've had such a great background. You've done 2 tours of duty at Department of Commerce, and we thank you for all of your service there, and spend time in private industry. You've got a very unique perspective on this whole topic, because you're both an economist, you understand the economics, and a policymaker, and you've given great testimony about some of the ways we need to be thinking about the semiconductor industry and controls around that. But can we talk for a minute about why legacy semiconductors. When we think of the big rush to get more fabs, we think of the advanced. We keep hearing about the most advanced nodes being in Taiwan. Tell me how you think about where the legacy semiconductors, as Andreas kind of gave us a good kind of a definition, or at least a visual for what that means. Where does that come into play from both the economic piece of the argument of what we need to be doing differently and the policy piece from both, if you will, a national security point of view?
Yeah, well, thank you again for having me here to join you. And I think you hit the nail on the head with the question. You know, where is this tension between national security and just economics, the sheer economics of competition? I've been doing, excuse me, industry competition for, 20 plus years. And when you think about, and a way to answer your question is, well, let me start off by saying the Department of Defense, national security, mission critical, Pentagon style capabilities, about 99.5% depends on these legacy chips, typically defined at the 28 nanometer and above level, right? It's legacy, mature, advanced, variety of terms. We'll call them legacy for today. And then on the commercial side, it's about 95% of the commercial market. Those are really big numbers. And when you look at industry competition, I typically analogize it to a pyramid. You have the commodity. I mean, these are complex pieces of complex components, but we'll call them commodity. It's the sales of the commodity sector, the commodity pieces that fund next gen technology, next gen innovation. Back in 2018, this is not difficult to predict China the way China plays in the game, because we have several decades of data and experience. It was pretty clear that China was going to run over capacity in semiconductors. And voila, here we are in 2023. It's building enormous fab capacity in China. It's engaging in overcapacity. And why does that matter? It's engaging in overcapacity at the 28 nanometer and above nodes. What it's going to do, and what it's planning to do, and it's what it's already doing globally, is depressing global prices so that every single company that makes the 28 nanometer chips and above, which includes Taiwan, South Korea, United States, et cetera, all of our companies are going to be losing market share to China. And that's the trick in terms of industry competition. Those things that national security ignores, because they're solely focused, the national security experts are solely focused on tech transfer, that's disjointed from the healthy economic base that we need to build up so our companies have the revenue to invest in next gen. Our company's revenue, TSMC's revenue, all of that to fund the 3 nanometer, 5 nanometer, whatever build comes from the sales that they have of the commodity side, the advanced, the mature nodes. And if China's running over capacity, to be sure, every foundry in the world is losing market share to China for this very reason. So what I really love to see the national security ecosystem focus more better on is bringing in national security with respect to economic security. Sure, we've got to block tech transfer, but we also have to protect the base that we have so that our companies are financially healthy and financially viable to have the revenue to invest in next gen. Unfortunately, on next gen technologies. Unfortunately, the US government has completely lost sight of us, which is why we see terrible policies in terms of, yes, focused on tech transfer at the most sort of advanced nodes to China. We're not even doing that well, but we've completely ceded the landscape to the advanced mature legacy nodes. And we're actually selling to China the equipment and the technology that it needs to build overcapacity to basically drown our industries. And I'm not really quite sure why the government is doing that. But when you look at it from the history of how we competed, we need the foundational building blocks of our companies to then be able to have the revenue to invest in next gen. And it's a long way of, it's one of the reasons why we see a lot of the global foundries across the world that have basically seeded the most advanced nodes, because there's no way to compete against China right now in terms of the revenue stream. If we actually stop that revenue stream, China gaining that revenue stream so we can rebuild at home, I'm confident that we're going to see some of our own semiconductor foundries now having the capital that they need to invest in not only the more sort of smaller, more advanced nodes, but even leap ahead technologies, which is where the US is pretty much also seeding innovation and market share.
I can
I'll
see
leave
that.
it for that for now.
That's good. Thank you, Nazak. Very helpful. I'm actually going to ask a follow-up question, but maybe to frame it, Kelly, if you can call up, I think we have one other slide, and we only have really two here, so you're getting all of the fireworks up front. But if you could put the bar chart up, I think this is a good footnote. And again, with thanks to the Infineon team, actually put the one prior to that, which is the bar chart, if you could. It actually will. Yeah, there you go. It's kind of the same data, but it's a little more visual. I think what struck me when Andreas and his team put this together, and it was directionally something I had understood and believed in, but it's sort of stark when you see it. The top, if you will, that orange is, at least in my colors on my screen, the very top bar anyway, is China. And these are all of the, if you call them advanced nodes at 28 nanometer, in this case 21 nanometer, but just to say it, in any of these nodes, the 130 nanometer, those are the very wide chips. A lot of automotive relies on those, power semis. But if all of these orange boxes represent about a third, I think it's about 34% for the first, 31, 26, something like that, that China is developing a lot of capacity in this, what we consider legacy. I want to come back to you, Nazak, right now on the economic piece of this, because if these are really many to the penny in some ways, that is, these are very, at the end of the day, landed cost or very cheap chips. Some U.S. companies might say, I hear you, there might be national security issues. I don't necessarily want to see my national security compromised, but I need to buy chips that I need many, for, the lowest cost possible. The capacity is there in China. How do you think about the economics of that? And maybe I'll ask you to talk about the tools that U.S. producers who do want to be competitive might have in a world where all this capacity currently exists. And by the way, it's only growing. This is Q3 23. It's only growing with 143 billion of support to the China industrial policy around semiconductor capacity development. So as these orange boxes become potentially bigger, how can U.S. Companies compete?
So the starting point is and you're absolutely right. Those orange bars are growing year by year, and which means that the market for semiconductors demand is growing, but the relative size of the other global competitors over time, and we're already seeing this happen year in and year out, our shares are relatively declining too. So China is capturing a greater share of the global market supply and certainly demand in semiconductors. So yeah, our companies are saying, I need to buy the low cost stuff from China. I want to stress something that's very important that people often forget in this debate. China's economy is fictitious. It's a non-market economy where the state determines land, labor, energy, raw material prices, right? And by us, the more trade we do with China, the more we're allowing China's market distortions to permeate throughout the rest of the economy. And it disrupts supply chains, it disrupts domestic capabilities in the United States elsewhere. So one merit for us, for the United States, our allies, to wean ourselves even off buying China's chips is just so we introduce less of those distortions in our economies, and we can actually start rebuilding an entire ecosystem that's based on a market-based system. There's more fundamentals that drive the economy, there's more predictability, et cetera, et cetera. So wean ourselves off that. But let's also remember, if we're buying chips from China, our capital goes to China. And just as a fun side fact, I just wanted to remind folks, China has the second largest GDP in the world, one of the lowest GNI per capital GNIs in the world, which means what? Our capital, the transport, it doesn't go to the companies, doesn't go to the workers, goes to the Chinese government, the CCP, which it could do to fund a bunch of terrible things like the build out of the People's Liberation Army and fund genocide. But putting even that aside, capital flows to China basically means less capital flows to American companies, the company of our allies. And by buying the cheap chips from China, right, we're not only, like I said, introducing distortions into our markets, but we're also taking capital away from the companies that we have in our country, our allies have in their countries to grow and thrive. And we need to really reshift our narrative away from, I need the distorted price goods, because that weakens the entire sort of global economy. We got to shift the narrative to, I'm going to help my allies build by trading more with our allies. Without question, whether frankly industry likes it or not, we are decoupling from China, and we are going through a gradual decoupling phase. And it strikes me as odd that everybody sort of accepts, when we have gradual environmental regulations, EPA permitting by 2035, by 2050, et cetera. But there's a sort of adverse reaction to making adjustments for us, our supply chains to be resilient by weaning ourselves from China. It's still the same type of growing pains and costs that industry has to incur. But let's make no mistakes, we are going to be decoupling. And one of the benefits there's going to be short-term pain, no doubt about it, like environmental regulations, et cetera, short-term pain. But the long-term benefit is that we are going to be integrating our supply chains with our allies. And when you look at any economic model of looking at doing that, our actual GDP growth, our wages, our innovation capabilities improves that much more substantially when we're trading with market economies and not a non-market economy where there's distortions in the market, and certainly unpredictability based on anything can happen with the CCP's one.
So got it. So if I can say that we've covered kind of the what and the so what about kind of legacy chips, both the use of the economic impact of purchasing. Let me bring Mark Harvey into the conversation. Talk about the now what. Looking at that last chart, we can say, well, let's try to put more capacity, both outside of any region. Let's not even make it about a China-U.S. issue, just from a pure supply chain. Having the supply chain, redundancy, supply chain, let's say integrity, to have chips closer to the source of use in manufacture. I'd like you to maybe comment a little bit, tell us a little bit about what Excite does, but also, start to talk about what it takes to build a fab. And then if you wouldn't mind, any differences between an advanced fab versus a legacy fab, and then pause on that, and then we'll tease out, US versus building it in the US versus another part of the world. But I wouldn't mind just kind of level setting when folks say, okay, I saw that last chart, I get it. Let's just build more fabs. Why don't we just kind of, get them going tomorrow? Can we have them up and running in the next handful of months? What goes into it?
So thank you, Don, and I appreciate the opportunity to talk about this because it is relevant and at the same time quite exciting in the global space. For those of you who don't know what Excite does, we are the world's largest design builder or engineer constructor of fabs around the world. We have a global footprint. We're a company in over 20 countries. We're over 100 years old, and we have the largest presence in market share associated with semiconductor fabs around the world. So happy to share some of that expertise. My role is leading the business unit that is focused in that space around the world. And we serve, of course, all customers across the portfolio and touch all the various technologies. So your question is very relevant. These buildings are basically the most sophisticated facilities on the planet in terms of the gases, the chemicals, the controlled environments, and all the specific requirements that go into the manufacture of the wafers. And to realize them and ready them for production is quite an expensive and lengthy process. And that's really regardless of the technology node being addressed. There are differences, but they're not specifically large needle movers in terms of the timeline associated with that. The biggest variant, the biggest determinant factor really is the geography where the fab is being realized, where it's planned, what the permitting regime may look like in that geography, in that municipality or that state or country, and then how supportive the labor rules, laws, the availability of labor, and that's a particular constraint as we rebalance manufacturing in the direction of the West. The labor constraint becomes particularly challenging. And the farther west you go from the legacy installs that we see in Asia, that becomes quite problematic. And then the installed supply chain to support the realization of those fabs. So in the US, you talk about somewhere in the range of 30, 36 months from the day you started your permitting process to the time you got your first wafer out the door. And for companies, that's an enormous level of time around the investment decision and the first dollar of revenue. So the tolerance for the capital intensity across that time frame until we get the first wafer out is quite substantial if we think about the US market. Certainly the timelines are more compressed in places like Taiwan and Singapore for reasons we can discuss, but those factors are very real, largely associated with geography as opposed to the technology.
And can you give us, maybe just paint a picture for us when we talk about building a fab? How many people are on a site? What does it take to kind of attract that labor? As Kelly mentioned at the outset, we've done some talks here at the center in the Wilson Center on workforce development as a major concern as it relates to semiconductor. But from the construction side, even before we operate and get a wafer out, how many people are coming onto the property?
Yeah, this is a very relevant question, and it's relevant for a couple of reasons. So fabs have grown. So the scale of the clean room space, of the manufacturing space, has increased substantially over the last, let's say, 10 to 15 years, right? Depending on the technology, it can be 1.5 to almost 3 times what they were 2 decades ago because of the need for the economy of scale, the efficiencies of production, and the buildings become more complex and a bigger effort to build. So therefore, a large-scale project that we would typically see planned around the world. Now, you're talking in the range of 5,000 to 7,000 workers at peak. Now, the important thing is, because that number is a little misleading, Don, that's at the peak of the manpower demand, if you look at a curve. But that's not to say that those people show up day one and they stay to the end, because as the project or the fab progresses, starting with your civils construction, your rebar, your concrete, that's a certain skill set, certain set of trade labor. As the project progresses, and eventually you're into clean room space and high purity piping for the gases and chemicals, that's an entirely different tranche of humans. So the trades and the skills progress through the course of the build. So while we may be at 5,000 to 7,000 at peak, you've probably cycled through the project 1.5 to 2.5 times that level of personnel to actually get through the required construction activities. So the demand, if you think about realizing in a country like Germany, where you have multiple projects on the drawing board that will stack, to find that level of skilled labor that previously was a reasonably dormant location in terms of new fab builds. And certainly Andreas knows this, Infineon is a big player in that space, but you've got a lot of neighbors that are coming to your neck of the woods that are talking about planning fabs. And there will certainly be a constraint there and other parts of the West looking to build in a hurry. Yeah.
So let me come back to you in just a minute. I want to go back to Andreas because this is a good kind of level setting. So we kind of understand what legacy chips are, what some of the economics around them, and even national security issues. And I want to touch on that one more time. But it takes a while to build a fab, so it will take some time to kind of right size that other chart that we showed. Andreas, tell us a little bit about how persistent are these? So if I've designed in 130 nanometers just to pick a node, do those chips last a long time in the marketplace, or at some point, how do you handle things like obsolescence? What exactly happens if I've designed an appliance, a product that I'm using some great feature, but I don't necessarily have a lot of physicists on staff. I've designed it in and I don't necessarily want to change it for a number of years. Or maybe it's an automotive application that isn't the high end, kind of entertainment or engine control module. Maybe it's just controlling a lock or a power window. I'm not sure how often those change. Give me an example of how you think about some of those older nodes, and how does industry kind of manage around that?
Yeah, so in a sense, some of the answer already lies in your question. In first approximation, it's a good idea perhaps to look at the end application. So if you have a fast turning end application, consumer electronics, just take the mobile phone again as an example, being replaced after 2, 3, 4 years, and contrast this to a car, which has a much longer lifetime, maybe not for the first owner, but for a sequence of owners. Or then think about large industrial sites. And one of the big opportunities, if I could just say that, is that as we develop more advanced semiconductors, simply replacing some of those those older semiconductors can give you, for example, significant energy savings if you think about equipping a factory. But that aside, yeah, you have essentially some factories which receive continuous investment, which really push the envelope towards ever smaller nodes, ever powerful semiconductors or new materials. But then there are also older fabs, which simply are run on a depreciated asset basis, and you get to much lower cost positions as time wears on, and eventually then perhaps not so much capacity is around, so supply and demand rebalance again. But the capacity can be available in the market for a fairly long time. The one last remark I wanted to make, though, is keep in mind that semiconductors are fairly small. You hinted at that, and so another possibility to manage the supply chain is that as products near the end of their economic lifespan from the perspective of the semiconductor manufacturer, you can simply manufacture a large number of them and put them in an inventory. And semiconductors are not perishable, so that's another way how to manage this longer tail of products. Yeah, but I mean, we have customers who are very, very faithful to us, where our design-ins last over 10, 15 years, and we have customers who want the latest and greatest, newest development every other year.
So the picture I'm starting to kind of paint from the conversation so far is that these are persistent. They stay in the market for a long time. They may not be, if you will, the most advanced that, you know, maybe somebody wants to go cut a ribbon and say, I've now built the most advanced fabs, but it sounds like I need them. It sounds like I need to have this supply secure, and I need to know that I can get access to it if I'm a producer and if I'm going to put it into my product. Zach, maybe I'll come back to you on that. You know, we had seen from, you know, if I took you back to last October 7th, it was kind of a watershed date, Department of Commerce, and some rules that came out on export control. Legacy was not part of that. Maybe, you know, you got to draw a line somewhere and you got to start somewhere. So compliments to those that, you know, started to at least get the dialogue going, I suppose. But tell me why Legacy was not part of it, or whether it should be going forward in some manner, given, you know, some of the topics we discussed, with sensitivity, of course, that we still have to make these for, you know, relatively competitive prices somehow in parts of the world where they may not have been made yet.
Yeah, let me start off by saying that, as I understand it, you know, 28 nanometers and above, these legacy advanced nodes, these are the ones that matter. From an engineering standpoint, with sort of the von Neumann style architecture that we have for IC chip designs, we're really just getting very little gains as these nodes get smaller, very sort of incremental, but much smaller. That's really underscores why these legacy nodes are so important. And, you know, great credit to the White House to push the envelope further. But I also want to stress that we are so late in the export control game on semiconductors. China was focused on indigenizing this at least a couple of decades ago. Since 2012, it really ramped up tech transfer, tech theft, pouring a lot of subsidies in this industry. And frankly, we just haven't really gotten our act together as a nation and collectively as an international community. So we're late to the game. So what does that tell us about these export control rules that came out, right? And this isn't an impeachment necessarily the Biden administration, it's just we're late and we're still taking small bites at the apple. When you are late to the game, you cannot go in really leanly, really small, in a small, strategic, nuanced manner, because you have a whole ecosystem that you've just seeded that you're trying to figure out how to gain back. Because remember, the ecosystem that we seeded was the 28 nanometer and above chip technology that China is very much capitalizing on to run over capacity to put everybody out of the market. All of the semiconductor manufacturers who need the revenue from the 99.5% of the market segment, commercial versus defense that I mentioned, if you don't have that revenue stream, you are not viable as a business. So That's why I'm very disappointed that we didn't actually put curbs on control. The other thing I really wanted to stress is that by us supplying China with the technology or with the chips, et cetera, at the 28 nanometer and above level, China has flipped the innovation versus sort of more of the worker aspect model. And I'm going to explain this further on us. 20 years ago, China was doing the commodity style labor for us, and we were focused on innovation. And now by us doing the commodity style stuff for China, China is shifting resources to produce those leading edge capabilities. The other thing I wanted to mention is that our export control scales, it's not, I see this narrative out in the press and the ecosystem about export controls don't work. That's nonsense. Absolutely, export controls work if our rules are weaved together in the right way, but they weren't. That's why China, we were shocked to see this breakthrough with Huawei's phones with SMIC chips in them. Absolutely, we shouldn't be shocked about this. I knew this was going to happen years ago. China was getting the deep ultraviolet, the deep ultraviolet lithography technology. There was still rumors that China doesn't have the extreme ultraviolet lithography machine to make the leading edge chips, but nobody was really concerned about the deep ultraviolet. It's not a choke point technology. The extreme is. The extreme is. So what does China do? The deep ultraviolet lithography technology is in many respects even more complex than the extreme ultraviolet lithography technology. China gets that freely, really without restrictions, hires engineers from the Netherlands, hires engineers from Taiwan, is able to build out this technology to now make 7 nanometers. Certainly, is the throughput somewhere between 40 and 60% not optimal? Absolutely. But you're talking about SMIC, you're talking about billions of dollars of state subsidies that they're getting. They're going to be just fine with about a 50% throughput. And anyway, that throughput is going to get better over time. You have to start somewhere where it gets better. So again, shame on us for not understanding and underestimating China's innovation capacity. The Australian Strategic Policy Institute just came out with a report of how China is leading the US in 37 out of 44 emerging technologies. This arrogance that I think America and the rest of the world have, that innovation is going to lead the day, and China's never going to be able to smart enough to figure things out. So we can let them have the technology, but as long as we have the revenue and run faster, I'm making this up like a hypothetical, but even if we got $10 million for giving some type of technology to China, that $10 million we have pales in comparison to the workforce that China's going to put at the innovation that we gave it, and the subsidies it's going to invest in the technology we gave it to really grow and dwarf the United States and the rest of the world. So our entire thinking about China's capabilities really underestimated what they were able to do, and this notion of we can run faster all the time. Let's make no mistake. Look at where China was 20 years ago and look at where it is now in terms of leading in technologies. China was always running faster. They were just further behind. And we need to have a little bit more humility and understanding that we have a competitor that is outsmarting us, outfunding us in many respects, much in the way because their economy is more nimble, their government is more nimble, and they could do that. And the only way to ensure leadership or reclaim leadership is innovation and very serious guardrails on transactions with China, because the more we transfer technology and capital, we are assuring our own destructions, and we have 15, 20 years of data, empirical data, to prove that that's been happening.
Well, I definitely appreciate that. That's quite the perspective. We're probably late in developing the capability set. So actually, let me bring Mark back into the dialogue on this one. So if you said it takes 30 to 36 months to kind of build a fab from permitting to first wafer in the US, is it faster elsewhere, and why? But let me ask you to kind of then turn that into what would you advise policymakers then, either at the local, state, or federal level? Because in the US we've got different folks that will touch the project at different levels. But if it's faster elsewhere, why is it faster? And then what are those? How can those learnings help to kind of pick up on Azak's point, to kind of make us go faster on the innovation side, make us go faster to kind of catch up on our side. Let's assume some of these other tools that she discussed will give us a little bit of time to go faster, but we still need to go faster. How do you go faster?
Yeah, Don, another very good question, because these are practical sort of boots on the ground realities, right? And it starts with the permitting process. And as Nazak said, other governments, particularly in Asia, and I can validate all of her comments because I lived in China for 6 years. The government actively supports there and in Taiwan and Singapore and those jurisdictions, the permitting process to be sort of a green lane functionality. They want to facilitate the investment. They want to realize this higher end of the supply chain in terms of the technology it brings, what it does for the workforce from an operational standpoint, the payoffs from a revenue generation. They see all of that. They're aligned to industry and work actively to facilitate it. So it starts with that process. The timelines for permitting in the East are roughly half of what you would see in the West. The US is variable because it's quite localized in terms of the permitting process, municipality to municipality. We'll come back to how to help some of that a little bit later. In Germany, as Andreas likely knows, it's quite prescriptive in terms of the permitting process. There's approximately 30 different regulatory industries that will touch a permit for a new wafer fab over the course of 13 months. It's quite robust in the amount of hurdles to go through and the challenge to navigate it. Whereas in a country like Singapore or Taiwan, you talk 3, 5, 6 months to get your project permitted. And that's materially different when you talk about the level of investment required and how much you have to wait in terms of time to get to first dollar of revenue. And then more substantial is the timeline for the actual construction time. So in places like Singapore or Taiwan, when you start the construction, you'd see either your first concrete or your first pile in the ground. At the time where you move the first manufacturing tool into the clean room space, you're in the neighborhood of 12 to 13 months. Yeah? In the United States, you're in the 20 to 26 months, depending on the technology that you're talking about, and also the jurisdiction. The labor laws, the labor availability, the productivity of the labor, all have constraints in terms of how rapidly you can progress. And whether that means labor law in Germany, which is restrictive in terms of the amount of hours worked, or the available labor pool itself in a place like the United States, where it's very difficult to draw from surrounding countries. Germany can draw labor from Eastern Europe and some surrounding EU locations. In places like Singapore or Malaysia can draw labor from Bangladesh, India, the subcontinent quite efficiently. So there's almost, let's say, a very robust to unlimited amount of labor you can bring to those programs to realize them. All of those are material benefits to the timeline that become attractive to owners when they look at siting the new fabs.
And is there, like an ombudsman role that you've seen in other countries that might be kind of a recommendation for, those that are trying to put these sites up more quickly in the US, just to kind of straddle all these different rules that you mentioned, workforce, community engagement, those kinds of things?
You can see in some of the more mature jurisdictions, which have thriving clusters of semiconductor activity, you see either the Economic Development Board or other government entities really sponsoring and helping shepherd the process. Yeah. Whereas as we talk about some of the Western locations where it may be virgin territory for a new greenfield site, you have permitting authorities, the local fire inspector who has never seen some of these really monsters of facilities before. So there's no frame of reference to think about, how do I permit this? How do I judge escape distances? How do I validate what I'm being told by this owner or by this contractor? And that tends to bog down because there's a lack of confidence, there's a lack of familiarity. And these are significantly hazard-filled facilities when you think about the gases and chemicals and the quantities that are required, as well as the environmental impact potentially if there's a leak or a spill or a fire. So there's quite a bit of, let's say, caution, justifiably so. But if you link that caution with a lack of familiarity, that also tends to bog it down. So I do think some form of shepherding process or ombudsman, as you call it, in these newer territories, I think would help facilitate a faster realization of the fabs themselves.
So it sounds like, yeah, please go ahead, Nazak.
May I also add, But water and energy, I mean, those are also big constraint factors. In terms of sort of workforce, obviously building a plant, and I should add, and I think you guys already know this, there's these smaller scale pop-up fabs that are easier to launch. You can create these kind of hub and spoke models. Perhaps permitting would be easier, but also in terms of workforce, innovations can go a long way in terms of simplifying the architectures for the workforce that we would need. And innovation is going to help us solve the water problem and the energy problem. And when a country like Taiwan can't really build any more capacity because they are really confronting a water shortage, a country that is, or a region that is surrounded by water, that underscores how important water is. And we need innovations to solve these really significant constraints in addition to the permitting.
So that's a good point. I'd like to maybe frame the last part of this conversation into that. So what's next, and how do we help policymakers? Some might be on this call, or some will learn from some of the dialogues like this. And I think it really is a good kind of advertisement to come back to these conversations, come back to them from time to time, come back to what the Wilson Center does in particular on these, and what all of you do in your jobs and other ways you've given these kinds of lessons before. So let me go to that point. I mean, there's a question that someone had asked, and I'll just reframe it a little bit differently, and that is, do governments, almost distort, what would otherwise be kind of innovation that should take place? Shouldn't, if I'm an automotive maker, or if I am a appliance maker, shouldn't I want to have access to, a economic kind of competitively priced product, particularly these legacy nodes? Do I want, there to be distortions in that? But maybe what I do want government to do is to innovate, is to find ways to make the market, want to put these fabs, whether they're pop-up fabs, I like that kind of concept, or they are, lessons that community leaders can learn from others, and how to create a fab environment, a campus maybe for fabs in new locations. But maybe, Andreas, I'll come back to you on this just for a moment on the economics, the economic piece of it. If you are giving any advice to policymakers on, carrot and stick, how do you incentivize the right, kind of opportunity to kind of put a legacy fab? If a mayor of a community came to you and said, I've talked to Mark, I know how to build these, I know what it takes, and I know from Nazak that I've got to do something to kind of help really foster the right policy environment. What advice would you give if you were suggesting to them that they put a fab in the legacy nodes in their community?
So let me go at it from a slightly different angle, because I think the question is almost too large to approach from an individual community. And some of the speakers and you yourself have said that really we are talking about an issue at the level of national economics or national security. The semiconductors have been dubbed the oil of the 21st century simply because they underlie so much of our economy, really, and try to make this case. So the question then is, to what extent do policymakers recognize that we are talking about a very foundational technology to our national security, to our economic well-being, to our progress, to digitalization, and how, against this backdrop, then are governments willing to use, and you said that, both the carrot and the stick. And I think the tools are available. It's about finding the right tool set, the right combination of carrots and sticks, and applying it not locally, but applying it together with like-minded nations, with allies, because the problem is too large for, I would argue even a very large and leading country like the United States to solve alone. It's something to be done in a larger context. And now, I've evaded your question. If you nevertheless indulge me and elevate it to that level, because again, I think the fundamental question is not one to be solved at a municipality level, but needs to be addressed at a higher level in Brussels, Berlin, in Washington.
I think that's a fair retort, and it probably does require a lot of interaction and learnings from one another and a lot of dialogue at all those levels to know exactly what to do. Let me pick up a different point that you raised, Andreas, on the depreciation of fabs. I think a lot of folks in this call might not understand the nuance of what you said, and I think Nazak gets this as well. It used to be, as I understood it, you'd build a fab, and then as the nodes evolved, you would put the next node in, and maybe you would build a new greenfield facility. The older fab then would produce something that would be more persistent in the market. And depreciated, meaning literally accounting wise, it costs less to now run that fab. But not only just accounting depreciation, but also you've got a trained workforce now. You could probably make those wider nodes, those older technologies, on a much more yield improved basis, using some of the framing Nazak gave us earlier too. It doesn't make sense for companies just to put in legacy nodes now without having kind of an advanced or a hand-me-down concept. Maybe you could describe a little bit of that economics, because it also plays into something Mark was talking about earlier about maybe a campus. When you think about campuses of semiconductor facilities, the way they're done in Asia, are there any lessons in how fabs are kind of, if you will, handed down for technologies that would allow this legacy that we've been using today's session to describe to be more cost effective?
Yeah, so very much so. And perhaps the one point, and Mark has mentioned that, but I want to stress it again, is the concept of economies of scale. You see this in Taiwan, you see it in manufacturing clusters like in Dresden now emerging, or some other sites in the world. Malaysia has some manufacturing clusters. So building your next fab next to your previous fab allows you to leverage the workforce which exists there, the facilities which exists there, and the whole ecosystem around it. So that is generally an advantage, and that is also an advantage which we have in many places in the world, in the US, in Europe, and in Asia. So that's the first part of your question. And because of that, yes, it is absolutely viable to build those fabs which you can call legacy fabs. And my company in Infineon, we this summer announced a very significant investment, many billions of euros, dollars, in the 90 to 130 nanometer node in Dresden. We did just a few years prior the same in our sites in Villach, and just recently now made an announcement in Malaysia, another important nation from a semiconductor manufacturing perspective. Again, multi-billion dollar investment. And by the way, this is not only Infineon. A lot of leading US companies, Texas Instruments comes to mind, for example, has announced plans with the support of the government, presumably, to expand their manufacturing base in the US as well. So there is some activity. I like, though, what's been said earlier. We shouldn't assume that we're leading the pack. In fact, we may be behind somewhere, and others might be a little bit more nimble. So this is definitely a pertinent topic.
Well, thank you for that. And just as a quick reminder to the audience, if we have a few minutes left. If you have any questions, please, send them in. And if we don't get to your question and you would like the Wilson Center team to kind of, direct it to any of us after the fact, please do. So let me, this picture that I've got painted now, these legacy chips, many to the penny, made in lots of places now, but predominantly in Asia. And it costs a lot to kind of, bring up a new fab to make a new one, but there are strategies that might make that work, just as you described. And there's some kind of lessons here for government. Nazak, maybe I'll give you kind of the floor for a few more minutes, just to kind of tell us, like, if I am producing chips in the US, but with the availability of more capacity in Asia. And by the way, this might not even be China. This could be another location. It could be another, maybe even a friendly country. But if I saw that someone had a cheaper cost and was, starting to just flood the market, if you will, with cheaper chips to create an economic dependency, if I'm in the U.S., what are my tools? What do I do? How do I address that? Because I don't want to build a fab that, as Mark has just explained to me, probably takes 36 months to put together, and I'll probably have to run it for a number of years to make my money back. How do I prevent, or what can I do if I start to see, like any almost commodity like oil, coming across the border and undercutting me?
Yeah, this is a huge danger too with the CHIPS Act, and then across segments with the Infrastructure Act. We're building a lot in America. And frankly, let's be honest about it, the reason we're doing chips, I helped draft part of the CHIPS Act. The reason we're doing the Infrastructure Act is to compete with China. It's all to compete with China. If it wasn't China, we wouldn't be investing so much in domestic industry, which I think America always should. But if we are building and China is going to be producing semiconductors that undercut us, what does that do to the value of the investments? And what the government isn't thinking about right now is, as we're building, what else do they need to think about strategically to protect the value of the investments that the government is putting in, but frankly, that these companies are putting in as well? And so there's a number of, so that's the threshold question. We're going to build and we've got to protect. Now, how do we protect? There's a number of sort of tools that will restrict, that will counter underpricing. There's, anti-dumping, there's Section 301s, there's Section 201s, Section 232 authorities. They're all, you don't all have to become trade experts in the next 60 seconds, but all of these tools are in some way import restriction mechanisms to basically level the playing field so our industry can compete. And it's not necessarily shutting anybody out of the market, but creating a more level playing field. And the one trick about each tools have different requirements. But one of the trick I hear people throw out the term anti-dumping in semiconductor discussions quite a bit, understanding China's overcapacity. And the one danger of that is that our companies, when there is an anti-dumping case, whether the government self-initiates or not, industry has to face off against China at the ITC and the International Trade Commission, the injury phase. Industries, when you look at all of the industries across the board that have been harmed by China, vis-a-vis how many of them actually bring China cases, there's a huge discrepancy, because the other industries that are injured have huge exposure to China that they don't want to bring the cases. So one of the things I'm working on is modernizing the laws so that industry can actually bring cases, but not but be protected enough through closed hearings, so that the Chinese or the other parties don't have to know who's bringing the case against them. So industries can still get the government to give them relief without fearing retaliation by China. And if it's not those industries and the customers, whoever else they deal with the China exposure, they can fear retaliation. And let's also just make sure that we all understand that we are in a climate where China is retaliating. China has been retaliating in terms of exports of critical minerals. And we've got to be really strategic about how we go and where we go next, and how we're going to deal with China's retaliation, which calls for more domestic investments, so China doesn't have that supply chain leverage over us. United States, other countries, you can't act because I'm going to restrict your supply chain access. We've got to be able to reshore, friendshore more, so China doesn't have that leverage, either supply chains or revenue stream, because China also uses the revenue stream we depend on as leverage to threaten us too. And we've got to disentangle ourselves. So our nation, the nation of our allies, we actually have the strength to protect what we need to protect and able to compete in the future.
Well, let's leave
Don,
it. Let's leave it there. Yes, go ahead.
Sorry, could just because this is just a great opportunity for me to build on and sort of bridge also from the very high level intragovernmental or government action, because there's also really something which companies can do. And there, I'm going to take issue a little bit with this, many to the dime, or it's like oil, because those semiconductors in many cases are incredibly advanced in terms of designing them into a system, say designing an electrical vehicle or designing a mobile phone. So there is an intense collaboration which requires a deep understanding on the part of the semiconductor manufacturer of the system, say the car, where the semiconductor is used. We call it product to system in our company. And that's really also at the core of where innovation often lies. So this process of a deep engagement between a semiconductor company and the OEM, the manufacturer of the consumer good or of the car. And there, if the companies, on one hand, the semiconductor companies innovate in being more integrated in those strong ecosystems, whether that's the car ecosystem, which you have around Detroit, or you have around Stuttgart, which I learned where you currently are. So that's something which semiconductor companies can do. And on the other side, then of course these OEMs can make smart choices. Really, in many cases, it's just a smart economic choice who they work together with, which are the companies which can bring this expertise and don't just dump something in their front yard. And I'm being a little bit melodramatic. So again, this innovation aspect of it, the working with, even if irrespective of what happens at the national level, what really happens at the economic, at the company level, at the entrepreneur level, I think there is also an interesting aspect to be looked at.
Excellent. Well, let's leave it there. I think that's an excellent way to end, because I think one thing that we know when you have strong competitors, whether they're state actors or other competitors, it makes you a better producer. You need to innovate yourself to find a way, and I like the innovation that all three of you have brought to the table today. Innovation in the rules. Nazak, thank you for being on both sides of private industry and government, and Mark for the innovation and how to bring some of the best lessons to our communities that would like to put fabs in their backyard, but would need to know the best ways to do that most effectively and efficiently, and from, as you say, pile to wafer, to sort of make it go as smooth as possible. And Andreas, what you said at the very end is the right place to leave it. We do need to innovate. We need to think about legacy semiconductors. They're a very important part of the backbone of the electronics industry and many other industries, and it's very important that we don't forget them, how they're made, where they're made, and how we foster continued innovation in them. So thank you to all three of you once again, and once again thank you to Kelly and the Wilson Center for hosting us and allowing us to have this conversation with all of you today. Please send in any other questions you have to Kelly and the team, and we'll make sure that we follow up if helpful. Thank you.